All right. Hi, everyone. I'm Brendan, and I'm excited to talk to you guys about some of my dissertation work, which is determining the relationship between the physical processes, waves, currents, things like that, and oyster aquaculture production. So this idea sort of started to stem back when I used to work on oyster farms, particularly it was rack and bag systems out on the Delaware Bay. And something that I was just noticing time and time again, I would go and survey the bags on these racks, and we'd have, bag by bag would be really nice. Then all of a sudden we get this one bag, that red bag up there, and we don't know what's going on. There's no real explanation, but just everything was growing poorly, and just that one bag, mortality and all sorts of things like that. And it really just drove me to ask this question, so what is causing this variability on such a small scale? And then coming from my background in biological oceanography, I thought, all right, it has to be something maybe with the physics. So I decided to kind of take that route and try to approach this. So if you look at this picture over here on the right, if you pass water through a bag, you have to interact with the mesh layers. You have to interact with the oysters, the oyster feeding, creating some turbulence. And then it has to go back through another layer of mesh. And that's just the interactions going on in one bag. If you scale this out cage to cage to cage, you have a lot of differences that are occurring from one cage to the next. And kind of thinking about that and then thinking about this variability in growth, and then sort of the industry understanding that's like, the idea of more flow, more grow, more dough. I think Ketchum Supply kind of, their tagline for their cages kind of really says it all. So we wanted to test that and see, well, is that really the case? And then what are sort of the caveats associated with that sort of ideology? So to start off, so there hasn't even really been a monitoring system to even determine what the flow is like inside of an oyster cage and how those cages are moving around in the water in real time. So we had to start off by developing these monitors, or starting to implement them. So we have accelerometers, which are about $80. They're the size of an oyster. So you could put them inside of a shell, and they're basically like a Frankenstein oyster you put in a bag, and it could tell you what the movement of an oyster is inside of a cage. And additionally, we have cloud cards, which have been around since the 60s. They're nothing new necessarily, but what they can do, it's something that you can make in your backyard. It's a plaster ball that dissolves as the water is passing by it. So the more water flow moving past it, the more this card's going to dissolve. You measure the difference in weight, and you get this sort of metric for water flow. So you could put these inside cages. You could put them in any sort of location and get a good understanding of what the water flow is across your farm if you put out enough of these. So then using those technologies, we wanted to go through a couple case studies where we're essentially trying to piece apart that relationship between the oyster and the cage movement, the water flow, and then oyster production, right? That more grow, more dough, right? So we start off by looking at biofouling mitigation and seeing how that affects the physical processes. We're looking at different culture methods in our second case study. And then lastly, modeling out a whole full-scale bottom cage lease where we're trying to see how that's changing across a farm. So to give you a little more detail, that first case study I was talking about, biofouling management, it's something we all kind of have to deal with. It's kind of a hassle, right? So we want to make sure that what we're doing is sort of the most optimal practice. So for this study, we grew oysters in long line cages for 8 weeks. And as you can see, they got pretty fouled up pretty quickly. And we had a couple mitigation treatments. We did nothing for one treatment. We just let them get really fouled up. The next, we would power wash, which we didn't have much success with that, so I'm not going to talk about it. And then we had desiccated oysters, so we would take them out of the water once per week for 24 hours. And then while we were doing that, we were measuring the motion of the cages and the oysters inside. We were measuring the water flow moving through it, and then the growth rate. And again, this is after 2 months. And what we were able to see was already some significant changes after that short time period. So we didn't see much of an effect on the water flow itself, but the cage motion, what I'm going to call jostling as well, we saw a significant difference between that. So in a fouled cage, the oysters weren't moving around so much in that cage because of that environment that the fouling created. And as a result, that environment created an oyster that was growing a lot more of shell as opposed to a desiccated oyster, or a desiccated bag, I should say. where you were seeing a lot more cage movement, and then you're seeing a better response in terms of the tissue growth of the animals. So just between these two methods of fouling mitigation, whether you're doing it or not doing it, right, you're sort of seeing this trade-off between faster growth or higher quality animals. And sometimes that trade-off is important. If you need to get your oysters out soon enough to get meat with a producer or something, and you're trying to think on a 3 or 4 month time scale, you can sort of work with these methods to get things out at an appropriate time. So in our second case study, looking at culture methods. So in Maryland, we're fortunate enough to be able to use a lot of different types of gear when we grow out. So what we wanted to do with this is trying to see what's changing as we move from bottom cages to something like a long line cage that kind of stays in the center versus a floating cage all the way at the top of the water. So with that, and again, I'm just going right into kind of the conclusions of it. Again, in this scale, we didn't see much of an issue with flow because it's all very small scale. But we saw this relationship with jostling, with the cage motion. And more importantly, we saw a difference between the frequency of jostling, so how much these oysters are moving around inside the cages, and then the intensity of the jostling. Are they just rumbling lightly, or are they really just crashing and crashing and crashing and causing almost some stress, if you will? What we saw is that if you start in the top left here, where you have a lot of movement, but it's not very intense, we saw something that would, like an environment that the long line systems produced in our farm. And that environment created oysters that had a pretty solid meat weight, so you were having very full oysters growing. On the other hand, if you move down towards the bottom cage one, not a lot of jostling, not very intense, it's kind of at the bottom, pretty protected. We saw a really fast shell growth rate, so something, time to market's a little bit quicker on those, but then again, you're sacrificing, maybe they're a bit flatter, maybe they're not growing as much tissue. And then lastly, the floating cages, they're sitting on the wave breaks, so they're not getting, they're a bit more resistant to some of the current movements, but the waves that are coming by are crashing on them. They're creating a lot of intense motion. And what we're seeing there, that it's creating a really well-shaped oyster. Again, at sort of the cost of shell growth and meat weight. So you could sort of leverage these systems depending on your location and what sort of product you want to get out. And I want to highlight for this, this system might change slightly from one farm to the next depending on your background environment. Ours was a pretty low flow environment. It was pretty calm generally. So this is kind of what we saw from our environment up in Maryland. And then our final case study, looking across a whole bottom cage farm. We wanted to kind of scale this out. So what we did is we grew the oysters for one growing season, April to November, across this farm, and we spaced them out. Each of those stars are bags that we sampled. And then on this farm, there was a really strong dominant flow. I mean, if you weren't paying attention, it would knock you over, like a really strong dominant flow going on. And then some boat traffic, because it was a residential area, coming across from the other end. So something that we were able to see as we were monitoring the growth of the oysters and then the physical conditions with using those cloud cards and those accelerometers, we're able to make these sort of contour plots where we can map out how the flow is changing across this one farm. And just want to note, like, this is something that you could essentially do with any farm. So it's very applicable to any sort of situation because they're, rough tools, they're pretty cheap, so they're easy to work with. And something that we can kind of note from our example, we saw that dominant flow that we kind of knew about. Then you can highlight that strong red band. Actually, I don't really have a pointer. Can I do this? Yeah, so you can see this really strong band here where it's not protected by the other oyster leases. And as a result, which is sort of interesting to me at the time, but it kind of makes sense, you're not seeing a lot of motion of the oysters. Figure the water flow is so fast, it's pinning them up against the wall, essentially, and nothing's really happening. So you can start to see those sort of relationships occurring by looking at it in this way. Additionally, you can start to factor in the shell length. There's some of the growth metrics, the condition index, right? How their tissue's developing. And you could start to see how the the growth the growth occurs in response to some of these physical conditions. Perhaps in this area where there's a lot of water flow and not a lot of motion, you're seeing kind of stressed oysters. They don't want to be pinned up against the wall, right? Where in other areas where the flow has been sort of protected by the center of the farm, we're seeing good shell growth and a medial condition index. So we can start to make these connections and essentially leverage this graphical data to try to optimize sort of what locations we're putting oysters depending on what we're trying to get at the end of the day, so we can get a consistent flow of oysters to our restaurants, to our producers, and things like that. So just to conclude some of these points, we're looking at these accelerometers and these clock cards. They're pretty valuable for monitoring some of these hydrodynamic or physical conditions across these farms. We're seeing that cages have water flow and cage motion have pretty significant impacts on quality across varying spatial scales. Maybe not so much on the one-dimensional scale, just one bag next to another, like I thought originally, but we're seeing it across this farm scale. So that's pretty cool. We're seeing that different culture methods are actually providing different, and I would think equally important benefits that we can correlate, again, to this physical environment, the motion of the cages themselves. And then I think what's most important, leveraging this relationship, now that we're starting to see that it's occurring, maybe getting some more numbers behind it and some additional applications, but we could start to leverage this relationship that we're seeing and really start to make management decisions based on our specific environment to try to optimize production and to improve the efficiency of production and sort of standardize the quality of the product that you want personally. So with that, I don't know if I have much time, but I'd be happy to take any questions. And if not, you can email me, follow me on Twitter for some research updates. So thank you.
Great. Thank you. Thank you, Brendan. Does anybody have a question? We do have some time for a question here. I got one from Stan here.
We got to get our steps in.
How is a clot card quantified? That's a tongue twister. Or is that just a relative measure?
So currently, the way that we have it set up, we're still developing it, but right now it's a relative measurement amongst the rest of that area. But I'm working on a model to try to convert it to something like meters per second or miles per hour or something like that, so then you can standardize it across different farm sites. But that's still under works a little bit.
Any other questions? Here we go.
So, Brendan, the color charts are really eye-catching because of the colors, right? Red to green.
Yeah.
And so, but for you, you're taking the measurements. It could be minute differences create that color change. Is there availability of sort of the quantification of those changes? I mean, is it really that great across the farm? I guess the basic question.
So in terms of the water, the acceleration, the motion of the cages, we're seeing a pretty significant difference. When we run the stats on it, they're significantly different. Whether they're minute or not, it's able to respond to whether it's minute or not. I don't, we're still trying to work on quantifying the difference between what creates what type of oyster versus another. So this is sort of our first look at everything. But we're seeing that, at least in these other case studies, that there is this difference between an oyster produced in this one way with this type of energy, and then it creates this sort of property, or this sort of oyster end product. So even if they are minute, we're still seeing differences in terms of the quality of the oysters or sort of that end product that we want to get.
Okay. All right. I think we'll move on to the next speaker then. If you have any other questions for Brendan, there's his contact information. Thank you, Brendan.
Thanks.